Okay, hi everyone. Thanks for the introduction, Chris. I'm going to start talking about how we are going to bring model-based reinforcement learning to novel robots and what we can do there. So to start, let's talk about robot learning. So robot learning has been big in the last 5 years. We've had some results at Berkeley with model-free reinforcement learning with visual input, solving some what seem like basic tasks, but this is a hugely complicated problem and a big success. And then we also have people setting up analytical problems and getting these robots from Boston Dynamics to do very complicated tasks, which is great. It's less learning here, but it's a huge success for robotics and we'll be moving things forward. And then we also have seen a lot of simulated tasks where you start with these complex bodies and the policies know nothing about the dynamics and they can learn to run, you can learn to walk, you can learn to stand up. And all of this is just from a couple simple embeddings of a reward function and we can get these complex behaviors. So what I'm interested in is how we can get these to work in more uncertain and new environments. So this is some very popular video from the DARPA Robotics Challenge in 2015, where we have these state-of-the-art robots from big teams, lots of engineering into them, and they failed for what seemed like simple reasons. So if we play them again, it's like it misses the handle and it misses the handle. So that seems like a sensing problem or just some feedback problem in uncertainty. These are all new environments for the robots and they're trying to do new tasks. And one that I would like to focus on is this locomotion task where this robot is trying to walk forward on a soft environment. And just this little discrepancy between what it was trained on could have made this fall over. There's a lot of things that go into it, but it seems like what should be a simple task for a humanoid robot, but it still failed. So I think we could improve how we deploy these platforms. And the context from my talk, as you've seen on the first slide, is going to be on novel robotic platforms. So in the last few years, we've had an explosion of new robots. A lot of these are at Berkeley. You have the Microrobots on the left, which from my group, and I'll talk more about some of those later. Then we also have an isoparametric robot from Stanford, which just means all the sides are the same length, like triangles. And then some other work from Berkeley with the jumping robot. We have a really small aerial vehicle that spins around, Piccolissimo. And then we also have some robots that are literally made out of found objects. So there's a lot of new robots, and I'm curious about if we could use some of these successes in robot learning to actually get these robots out into the wild and doing simple tasks. So what we have are novel robotic platforms and what makes these problems a little bit different than some of the big robotic systems that we have. So what we want to do here is really demonstrate control for the first time. If you have a new robot, you're kind of like sending it out into the market and you say, we did it, when we could say we got controlled flight, we got it to walk, we got to do some simple tasks. But in these robots, they're hand assembled by grad students or engineers. So, okay, I'm gonna change that. But we have these two issues. The first is that we know how they work in theory, but when we come out into the real world, there's not a strong prior on the dynamics. So there's this gap between the assumptions we made to design the robot and then what actually happens in the real world. For one case, like the Ionic craft, we have these wires that are really difficult, or we might have motor non-idealities in something like the found objects. And then really just nonlinear dynamics and higher order terms that we don't consider can be really dominant at some smaller scales. And again, when we're making these robots by hand, there's a huge cost per test, and some of them might not be robust. So I think we need to be able to learn faster and generate control faster in order to use them on novel robots. So these are 2 points I'll come back to. Let's think about how we could actually get to learning a controller for a robot. There's a lot of options, and we could kind of think about, we could use system identification with state space models to try to learn a model of the robot that'll give us an effective controller on a bunch of tasks. Or we can use some knowledge of the robot and do PID hand tuning. And then there's some newer methods such as model-based reinforcement learning and model-free reinforcement learning. So all of these methods have their pros and their cons. And I'll talk about the decisions between how I focused on one of them and why I did that. And generally, we can think about two divisions. The first one I'll start with is that we have model-based methods and model-free methods. So essentially, we can either try to use some information about a robot and try to learn some information about the world, or we can just think about generating a policy that'll explore the environment and figure out the pros and cons of different actions on its own. So let's look at these two decisions and where the related methods might fall. So these are kind of the grid that we can have for learning control. You can see I have this first decision, model-based versus model-free, which I will be going into more. But then there's the second distinction that I make between some of these methods. We have an analytical and offline method, which is kind of using our physics-based knowledge in order to solve model learning for control, to try to get a controller based on what we know. And then we also have data-driven approaches, which are these newer reinforcement learning approaches that are trying to iteratively learn online and see the data of the world. And then what we're going to get is a controller that iteratively improves. So let's look at each of these quadrants. On the top left, we're going to start with model-based RL. And there's a couple different control paradigms we can use. There's a couple papers that do some version of model predictive control on a learned model. Model predictive control is from the control series theory side of things, where you either sample a bunch of actions and pick the best one, or you can solve with Bellman updates from the receding horizon to get the optimal action. And then there's another series of work that's coming, which is you learn a model iteratively, and then you use other control or reinforcement learning methods to generate a controller after the fact. But all of these rely on a model, and they're generating data, they're gathering data over time. And another way to gather data over time is what is called model-free reinforcement learning. And there's a lot of varieties here. And what we can see is that I'm adding a note because I see something weird and I want to fix it. Okay, this might not. I'll just look at it later, that's fine. And model-free RL, we have policy-based methods such as soft actor critic and trust reason policy optimization. We also have tabular methods that are like Q-learning based methods and approximations. There's a lot of model-free RL. It's been having huge success recently. I'm not going to go into all the details, but it's something that we can consider because it shows strong performance, and it is getting less sample hungry. But again, to the next quadrant, we have now more offline methods where we're going to try to generate a controller in a closed environment and then send our robot off into the world. So kind of the baseline for a lot of people working in areas like me is just like a tuning heuristic where we can try to tune PID control. And what we need to do that is to have some basic understanding between the forces of the robot and how that relates to some state variables we have. And that's a really powerful tool. PID control is used in a lot of environments. It's very simple, it's computationally efficient, and that's why people use it. And then in the same bucket, we could do something like system identification with classical control. So system identification is gonna take a series of trajectories in a controlled environment to try to generate a model. So we have state space models like x dot equals ax plus bu, and then we could do something like deriving LQR or linear quadratic regulator on top of that. So that's the difference here we'll go into more, but we also have the last quadrant where you assume nothing about your model, and then you also just do it offline, so you have no knowledge and you do it all offline, which kind of sounds like magic, and you get a controller out. So I'm going to go into how we decided on which of these quadrants to use for novel robots. So the first decision that I made, again, we're thinking about novel robots, and we're going to be working in uncertain environments where we might see some things new and we might have distribution shift from our original training set. So if we think about model-based and model-free methods, kind of we can look in the context of reinforcement learning, but the model-based benefits also extend to the analytical methods. So this is just slicing around along one axis. So we see that our model-based methods are known to have, we have offline planning capabilities, generalization, and are generally sample efficient because what we're doing is we're taking samples from the world and we're trying to build a model. And then once we have a model, we could run computation offline to try to see what will happen if we take a certain action or where a model will lead us. But this can be more difficult to implement and computationally intensive. And on the other hand, model-free methods kind of mirror this. So instead of planning, you get something called a reactive policy. A reactive policy sees a state and takes an action, which can be a pro and a con because it's a little bit more computationally light and simpler to implement. But these methods starting out tend to be task specific and data hungry. So kind of where we decide with these new robots is the biggest items that we need are sample efficiency, and some offline planning capability is really great when we're working with new robots and we want to verify some of our dynamics. So I'm focusing on sample efficiency. So we think we're probably going to want to do some sort of model-based method here. And the other idea is, do we want to do an iterative approach or an analytical approach? So the trade-off is between we're going to collect data online and see where we're getting and try to retrain and improve versus an analytical method that's trying to just use the decisions we made when we were making the robot and then get a controller from there. The pros of the iterative methods are we don't require a strong prior and we can incorporate distribution shift. So it's really important, and I'll come back to this, but you compare this to analytical methods. That the pro of that is if you could get analytical methods to work, you generally don't have to test as much there's no extra testing once you have a controller. You don't have this iterative approach, you're just one and done. So if it works, you've demonstrated success and it's great. But there might be some assumptions that are limiting the performance of these analytical methods. So we're leaning towards the iterative method to try to deal with these new environments when we're taking a robot we made out of a nanofab and into the real world. So where this puts us in the quadrant is model-based reinforcement learning, which is an iterative approach, and we're building a model. And this generally this framework works by an agent acts in an environment, and then it learns the model, and then it uses the model to plan actions to maximize reward. So you can look at step 3, formulate the optimization problem. Is what we're doing is we're taking the action that maximizes the sum of discounted reward over some time horizon. We're trying to plan a trajectory that does the best it can. And this is offline and different than distilling a policy, and we're planning in some dynamics that we know. And the model is going to simulate these dynamics. And in the context of model-based reinforcement learning, what I'm going to do is I'm going to make a series of claims for what do we need to do to work in these new robots, and robots that are going to be tested in a substantially different environment than when they were designed. So the question is, we have this loop in the last slide, and the question is, do I need to improve the model or improve the controller to make this work? And I'm going to argue that we want to improve the model to get some simple tasks accomplished on new robots. Basically, start with, we need a model to learn anything. So if we're going to go into the real world with some of these robots, we need to have some model to even do a basic control task. And realistically, compared to some of the advances in reinforcement learning, we're working in a lower dimensional space. So these tasks are relatively simple. We're not pushing the limit with many contact forces and a lot of complex dynamics to do dexterous tasks. I'm thinking about locomotion and simple tasks. So what these mean is we don't have to do a lot of reward function tuning. We don't have to worry about dimensionality as much. And we just need a minimum model to do a simple locomotion task. So what I'm proposing is we have this challenge where robot learning is not sample efficient enough for some robotic tasks on things like the Ionic, Salto at Berkeley, and other new robots. And what I propose is to improve the dynamics model in model-based reinforcement learning by focusing on model task pairing and how the model could be improved to improve a task, rather than just focusing on training a model that is accurate. And I'll go into this, and this is something that I converged on, but ultimately I think improving the model is the limiting factor for getting some pretty breakthrough results in new robots that is also with model-based reinforcement learning. Okay, now I'm going to go more into specifics of problems that I'm interested in. And this context starts with microrobots. So here, these are some of the robots I showed on previous slides. And what you can see is all these 4 robots are made in the group, and they're all really small, smaller than a coin. And they're made in silicon nanofab, but then we hand assemble them and solder wires to them and put IMU boards on imperfectly. And they look crazy when they fly like this, where you have these wires coming off that impact flight. This is open loop flight from one of our earlier papers on the subject. And it's a hard control problem because so much changes from when we're designing them to what actually happens. And specifically, again, there's high cost per test. Getting this video with the IMU on board was a huge success at the time, even on one robot. It takes hours to build a robot. And there's these unmodeled dynamics in the wires. So let's look at the Ionic a little more closely and then talk more about learning for control. So the relevant details, if we zoom in on a microrobot, is that it's about 4 centimeters squared. It's 30 milligrams. So if you poke it with any human forced finger, it's going to shatter. Super light. It works with this mechanism that's called electrohydrodynamic thrust, which is ultimately an ion thruster. So it ionizes air around a high voltage, and when you create ions, they're in an electric field. Ions move in an electric field. They collide with neutral molecules. Those neutral molecules have mass, and then you have a momentum transfer. And a couple more things is that we have this experimental control setup. We have a whole stack of power supplies. We need to wire this up by hand. And then we get these wires that are impacting flight, which are really nonlinear. They change a lot. So we want to learn online to generate a controller for the Ionic really fast. Okay, so I've started with my introduction and motivation. I want to learn how to control new robots really fast, and I think that improving the dynamics model is the place to start to do so. And now I'm going to go into a bit of work I've done that shows that we can do some of these things, and then think about where we need to improve this framework and talk about where I'm going to do this in future experiments. So to start with, we wanted to learn to fly with the Ionic. That's the goal I've had kind of signposting out into the future. And we see that it has 4 thrusters like this and IMU on board. And we're like, what could be a bit simpler task as a proof of concept that we can do a complex nonlinear control. So we use the Crazy Fly, which is an off-the-shelf robot, off-the-shelf quadrotor that also has 4 thrusters. It's lightweight. It has the same IMU on board. There's still a cost to test. It might not be as high, but hopefully this is a demonstration of if model-based RL is the right direction. So what we have is this learning system where we have this loop that I showed earlier where we're learning a model and then we use that model to evaluate control. And we have a specific task in this case, which is to minimize the Euler angles pitch and roll. So we want our robot to be flat in the air, and we're working with onboard state values only. So we're working with yaw, pitch, and roll, and then linear and angular accelerations. So what you can see here is we don't have any global estimates. So as long as the robot is planted and flat, it might drift, but that's okay. And then we're applying direct motor application, or doing direct motor application of PWM voltage. So what this means is we turn the internal controllers off, we apply a voltage directly, which is how the Ionic will work. The test setup, we have an Arduino, it sends voltages directly to the Ionic. We want to mirror everything here. And again, this is just trying to be like the Ionic. So let's watch a video and see what this looks like. And what we have is that early on, the robot kind of just barely gets off the ground, and then we'll trigger its angle max. So if it goes above 35 degrees, it will turn itself off to avoid damage. So then over time, we collect more data points, and then very rapidly, we get to this final performance of less than 10,000 data points, so about less than 1 battery life of a robot, and it gets this controlled flight with onboard data and this sampling-based model predictive control, where we're trying to minimize the pitch and roll. So you can see here, it looks pretty stable, it drifts away, and here we go. So let's talk about the decisions that actually made this work. So we had a bunch of design decisions, and generally in model-based RL, it comes down to the dynamics model and control. So what we have here is a lot of decisions that go into making a functional controller. Talked about this in the design choices early on where we arrived at model-based RL, that it can be tough to implement. So this is kind of what we have to do to make it work in our case. We have to decide which state variables we want to use in the dynamics model. There's things like, turns out battery voltage isn't helpful in making predictions on this robot because the motors determine the battery voltage locally over a short flight time, which is kind of funny, but, and things like which loss function when training the network and all these model parameters. So this is kind of where we arrived at. We did a trick where you append the history of the state to the inputs of the network to try to account for things like motor spin up. So essentially the time constant of some of the dynamics in the robot are longer than 1 time step of our discretized dynamics. So we need to incorporate some history. And then we have this probability of a change in state, which ultimately we can constrain this variable and make this small with our loss function in order to reduce the variance of predictions. And then at control, there's a trade-off between frequency and model parameters that we have. So the sampling-based control is primarily determined by the prediction horizon and the number of samples that you use. So these number of samples are passed through the neural network and we predict over a certain horizon. And then these numbers, if we do more evaluations, we have a lower frequency. But if we have a lower frequency, our controller is less reactive to perturbations, and a higher frequency, we have less planning capacity. At higher frequency, the planning capacity is doubly mitigated because when you're sampling faster, the delta t is smaller. So the delta t is smaller, and also you can predict on a shorter horizon. So that's a benefit of low frequency, is you can plan multiple seconds into the future when your delta t is smaller, and you can predict more steps of the neural network, which is really how we ended up in this sweet spot, which was around 50 Hertz, where we have another reactive policy, but still enough planning to choose the best action sequence. So why does this actually matter? So we showed control flight here, and this was one of a few demonstrations of model-based RL on real robots, and it was the first flying robot with all low-level control. And it really is a challenging control problem at low frequencies. The onboard controllers for these robots operate at about 500 hertz or more, so this is a really different paradigm for control. It's not to say that it's a direct competitor to PIDs, but it's a step forward in a bunch of related works for model-based RL to show that sampling-based MPC can be applied to a hard problem. So I want to compare what other people did to what I just showed you to make it clear that this is clear the contribution of this work. So we have Williams et al. That shows that you can race a car around a track with model-based RL. They have a variant of the MPC that involves some information theory, and it's a model planning path integral, which is just a little bit different formulation of the cost. And then you have two related works at Berkeley from Anusha. So you have this other walking robot where she used image condition dynamics models to control and walk trajectories with this robot, and they had similar model predictive control setup and number of samples required. And another work from Anusha where she used this type of setup with dexterous motion. So this needed an improvement to the sampling mechanism of the controller. And what's kind of different in these last two is that you have contact forces. So the contact forces can be difficult to model, which is kind of like pushing the model and pushing the controller to a higher limit. But in our work, we're working on something where there's really high cost to test. If you mess up when you're controlling the crazy fly, you're gonna flip over really fast, and it might be unrecoverable. It might reach unrecoverable states a lot faster. So this is really showing the planning capacity with a simple model, and that we can still get to learning here. And I think that we want to learn even faster because there's still a lot of cost and still a lot of crashes when we're learning with the crazy fly. So this is kind of the end of where I'm talking about experiments that I've done. And now that we've learned a lot of things along the way for showing that we can do this on a new robotic platform, there's a lot of things there where we can improve model-based RL. And this is a big part of the exploration for why I think improving the model is so important. So let's look at this little framework. Right now, it works on a bunch of applications, but I think things can be improved. And as I said, I'm going to talk about the dynamics model. So right now, when we're using the dynamics model for control in various regimes, a lot of what happens is we're predicting trajectories on a learned model. And what this means is F theta is parameterized by a neural network, and then state is a value, and then action is what we choose. And we choose predictions over time. So, or we look at rollouts of predictions. So at time step 2, we have this repeated evaluation. We repeat the evaluation again, and then we can have a general form. The general form is saying that we have a lot of compounded network passes. And people who study neural networks show that when you're repeating an evaluation of a neural network on a shifting distribution and a neural network that's trained on finite data, it always is, you get these diverging predictions. And these diverging predictions are really dangerous to sampling-based control. For a lot of reasons, depends on your reward function too, but diverging predictions are not something that we want to be choosing actions from. So this is just like a first pass of, this doesn't seem great, and this is why we have to trade off between prediction horizon and number of samples. If you make your prediction horizon too long, all of your predictions are going to be somewhat bogus, and then there's a lot of challenging factors here. So what I think is, I want to think about what is a better dynamics model. This is really broad, and in the past we've just been focusing, a lot of research is focusing on one-step predictions and making sure these work for the making sure these predict accurately the dynamics. But you could say a lot of different things. You could think that short-term prediction accuracy is useful. So something like model-based policy optimization uses one-step predictions to feed into a soft actor critic algorithm. That should use short-term prediction accuracy, but also sample efficiency, which I've talked about a lot. How quickly can you learn a model? And is it computationally efficient? So if we start ensembling models, we're going to have a linear increase in our computational burden. And is it easy to train? Or is the long-term prediction good? This connects with classical control a bit better in receding horizon. And also, is it generalizing? I'm focusing on one task most of the time, but we might want to use our model for multiple tasks. So what I would claim is that we want to kind of think about where the models came from, and then we can start to enter what type of model we want. So model learning for control has its origins in system identification, where you want to gain a complete model and then learn control. So here's a series of elicitation trajectories. And with these elicitation trajectories, you try to learn a complete model that covers the space you need for a task. You might not explicitly know what you need to do a task, so you might have a whole bunch of trajectories. In reinforcement learning, an iterative framework, what we do is we observe task-specific data subset and we iteratively learn control. So this gives a different distribution. Depending on the assumption, depending on your exploration in the iterative method or on your assumptions and system identification, these two plots could look more similar. But in RL, we generally have a distribution around a trajectory that reflects our task. So how do we actually learn a model with this data? So what we do is we have a few moving points in model-based RL. This is just a different visualization. We have a dynamics model, we have a controller, and then we have the environment. The environment here is kind of the last step, which gives us all the data that we need. And it gives us these trajectories. And what we do now is we train a dynamics model only on the transitions. And then the policy is generally trained to maximize this reward. And there's kind of a disconnect here. And what we see is that what we get is that we have this assumption where when we're training models, the assumption is that we improve the accuracy of our model or we maximize the log likelihood, we're going to get a parallel increase in our episode reward. But what we're really looking at is a dual optimization problem. And when we have two optimization problems, we're running some solver here, there's not guaranteed to be numerically a correlation between these two. So at training time, we're maximizing this log likelihood, and at control time, we're now maximizing the reward in a different step. And my argument is, if we want to improve the baseline of model-based RL, we're not currently doing anything to make the model act for us, to act in a way that we improve reward. We should be making our model improve reward in some way. So this is what we call objective mismatch. Objective mismatch is the mismatch between these two objective functions. And in model-based RL, we want to link them so that we can solve tasks faster in my interest, and then also so that we can solve more complicated tasks and push the limits of model-based RL. So let's think about this assumption. The assumption is that if we maximize log likelihood, we'll maximize episode reward. Where does this take us? We could do something where we could visualize some dynamics models and look at the log likelihood when training them on a test set versus the reward they got in a task. So if this assumption held, we would have this really tight-knit relationship where as likelihood increased, as our models were getting heuristically better in training, our episode reward would get higher. And there would be this tight correlation and things would look good. And we could use this as a design tool as an engineer, and we could just incorporate this into our training mechanism and we'd be happy. But what happens when we look at real data? So what we looked at is we sampled 2,400 dynamics models used for control in a half cheetah task, which is a simulated task. And we looked at the likelihood that they received on a test set and then the reward they got on a task. And this is evaluated on 3 different data sets relating to the assumptions for learning models for control. So from left to right, we have an expert trajectory. The expert would be like that line in the iterative learning where the data follows the trajectory perfectly. So it's just sampled from a solved controller like soft act or critic at convergence, and we see how the different models predict those points. And there's a discrepancy already. And then on policy is just the iterative data collection from the model-based reinforcement learning loop that I talked about, where you just keep aggregating data. And then global is trying to model something like system identification that gets a complete model. We sampled points from the entire state action state action space, and then evaluate models on them. So you can see on the outsides here that the models that are used for control don't just predict the expert trajectory, which is fine, which is good. I'll talk about this more. And they really don't predict the whole environment. So the idea that training a model iteratively in the current model-based RL frameworks, we use the PETS algorithm for this one, and that some of these assumptions might not hold true. We're not learning the whole environment. And in the on-policy case, we see that there is a loose correlation between likelihood and reward. But consider this, if you're training a model, say you train a model and you get a log likelihood of 2. Your code returns this number, This could put you anywhere. It could put you from low reward here to high reward. And you don't know whether or not the model you trained is going to be one that gives you high reward or low reward based on your log likelihood. What we want is that if you have a high log likelihood, or if you have a high training metric that we can change, then you're going to get high reward. What can we do about this? So a couple initial methods are, one, a simple one is to train the model prediction to, instead of predicting one steps, to predict steps that are all from the same trajectory. So we can see is from the original on-policy data, if we instead evaluate a model to see how well it predicts trajectories, so the same data, it's the same data set but organized as trajectories, what we can get is a little bit better correlation. So you get a better correlation coefficient. So a rho equals to 1 is a perfect positive monotonic relationship. So the correlation coefficient increases, and also visually it kind of slants over and is tighter grouped, which is easier to use as a training heuristic for an engineer. Another idea is to reweight the dynamics data around a task of interest. And what this means is we know that our data is from some overlaying distribution. And what if we prioritize points that are on or close to the expert trajectory and then ignore the points that are further away? So what we've seen is that this can kind of improve sample efficiency, but it's at the cost of generalization. Let's go back. Now we're going to talk about model task pairing specifically, now that we've seen that there might be some issues in the current model-based RL framework limiting performance in certain ways. So back to the question, what is a better dynamics model? So if we wanted one to be sample efficient, we could do something like this reweighting of dynamics data that I mentioned, but that might not be the only goal. What if we want it to be computationally efficient? This will lend itself very nicely to the Microrobots and some other new robots that I showed early in the slides. We might want to do some data processing. We don't want to train a huge neural network on a huge data set there. Or what if we want long-term prediction accuracy? This kind of matches with the planning-based control that we've been using in the past, but it also extends more broadly to other potential control mechanisms. So if we want this, let's think about a new model where we're matching our model with what we want it to do. We want it to predict long-term. So what about a model for predicting trajectories? Here's an illustration for one-step compounding predictions where we have a trajectory and we slice it, and then we collect these steps. The training points correspond to this equation where we have a function parameterizing a change in state. But let's propose this new method. The new method is a trajectory-based model where instead of conditioning on an action, you're conditioning on a control parameter. So the control parameter could be something like LQR or PID, some other finite control parameters, and then also a time index. So you start at a state and you train on each future reach state based on the time index and the controller. What you get is a lot more points, and they're more focused towards the end of the trajectory. So I should change the order of this, but there's a lot of related works in predicting trajectories, and a lot of them are using Gaussian processes because neural networks are not as optimized because of this compounding error thing. So I'm going to move this slide earlier, one slide earlier for anyone that watches this recording and is technical. I'm going to move it before I introduce my new neural network parameterization. So think about this trajectory-based model. What are the key takeaways? Well, it collects data points at a rate of t squared. You get that by taking the sum from 0 to through all of the initial states from the index to t. So it's really t times t minus 1 over 2, but it's related to t squared. You get points twice as fast at a square relationship where the one-step models are a linear relationship. And then we've seen in initial experiments is that you get long-term prediction accuracy where the dynamics converges to this endpoint. And then also it's conditioned on control parameters. So you're then learning in a different space than if you had actions. So when you're sampling actions and training on actions, you kind of want your action space to be covered. But when you're conditioning on control parameters, it's going to be a different space where you might have more, you're probably going to have more, you can have more dimensionality, but you could have more control of what's going on there. And we could talk about that more later. So with these models, what we've seen is that, as I've said, we run experiments. The trajectory prediction model has uncertainty in the middle, where the trajectories will vary a lot as there's oscillations in the controller. We use PID in our example, but at the end, it'll converge to the set point. Where in traditional models, there will be this divergence of predictions because of the compounding network paths. Let's look at a specific example. Oh, that needs to be deleted. A specific example for a reach or task is that apply a PID control to the reacher at each joint, and then we see where the end effector will go. We're not trying to solve the task, we're just looking at the dynamics and trying to model the dynamics with the controller. And you can see here, these one-step predictions all diverge within a couple hundred training steps. Look at the log scale here, but our trajectory-based models converge over time, over long-term predictions. So what we want to do with this, we have a deliverable where I want to show that we can predict trajectories of length of 100 over a length 100 with neural networks. When we're doing sampling-based control, we don't really go above 20 to 30 prediction steps. And the impact of this is a new tool for learning control in robotics. Right now, it's not ready to be integrated in online MPC because we're conditioning on control parameters rather than actions, but it's a step in the right direction towards fitting our model towards the controller that we're using and the assumptions that we have. Okay, now I'm going to talk more about what I want to do with the fact that we've improved models and we want to use this for control. So there's a couple experiments in model-based RL that I want to do. To start with, let's go back to the Ionic. We want to control this new robot. Here's a video of a control attempt where we have a little bit thicker wires on it, so the dynamics are more influenced than what we'll do when trying to evaluate for true controlled flight. For true controlled flight, we need the robot to be able to flip itself over in open loop, so we know that it's controlled. And here, you can see that the dynamics vary, but a weakly tuned PID controller can work pretty good. And what we can get there is we can get a data set. I'm going to compare the dynamics model predictions for an Ionic data set to a dynamics model predictions for that worked on the Crazyfly MPC. So here you can see, I've showed this formula a lot, where we have a next state is proportional to the dynamics model. Here we're looking at one dimension, we're slicing in one dimension of our state action space, and we have black is the ground truth. So every time you take a robot arm through the world, you discretize the steps. If you look between the two steps, there's going to be some change in each of the state variables. They're continuous variables, so there'll be a change. So here, the black is that change, the true change sorted. So we sort it from low to high, and then at each of these points, we look at what the neural network predicts. So the neural network is trying to match that prediction, and there's a noisy trend in some areas in the middle that aren't great, but in general, it works on the test set and the training set. So what does this look like for the Ionic? The Ionic looks pretty good on the training set, but the test set has a couple issues. And the test set having issues at the edge of this range, and even in the middle, it doesn't look fantastic, but edge of the issue means I don't think there's enough training data yet for this method to work as is. And this was a pretty good test environment for the Ionic. It was a long flight. This is kind of the amount of data that we're going to get. So this was trained on about a quarter of the data than the Crazyfly. The Crazyfly is about 10,000, the Ionic is about 2,500. I want to be able to make that work. Another method that we could try for the Ionic is trying to learn to fly just in PID control. So don't learn a neural network, just try to iterate on PID controllers. And there's related works that have shown that this can work in other robots. But this might take 20 to 50 flights to converge to the right PID parameters, because Bayesian optimization is trying to explore the state space. It's not local iteratively improving directly. It's trying to get a global function that fits the state space of PID parameters. So I'm wondering if we can try to merge the two. So to learn more rapidly, I want to try to leverage a deep model as a simulator and then use this optimizer to extract control. So what this would look like is we have a bunch of logged experimental data, and then we want to predict on this dynamics model to learn controller. There's a lot of related works that have started doing this in model-based RL, where we have a state-of-the-art algorithm that uses short rollouts in the simulated model to train a model-free controller, and that has showed great sample efficiency. And then also this model-based actor critic was used to create a value function on the simulated model and then fly a robot. So there's a lot of related works that shows people doing similar things, which is more leveraging the dynamics model. Use the model a little bit more. So what am I gonna do? I'm gonna do something that I call model-based control distillation. So what we're gonna do is we're gonna collect experimental data. You can log the IMU data from this robot, and then we're gonna train a dynamics model. We do this once. We do this, we collect the data, and then now we're gonna have this iterative simulation phase. We might need to go back and get more data to deal with distribution shift, but we're going to simulate trajectories conditioned on a controller, and then we're going to optimize the control parameters. So there's kind of this feedback loop in simulation where Simulation will send some reward function to the optimizer, and the optimizer will send a new controller back, and we'll stop when that converges, and we'll take it back to the robot. So the difference is here that we're taking the dynamics model and distilling it into a classical controller rather than a neural network policy, because we think it lends itself to the problem well. So the impact of this is that, or what I want to do is use this to control the Ionic graph for 10 seconds. And there's a big impact here in a couple different communities. It would be the second ever controlled flight of a flying microrobot with the Robotic at Harvard. And then also bringing model-based RL to a robot with even more increased cost per test will encourage more applications of this in the area of novel robotics and show that people can do this. Okay, next experiment. I want to use what we know about model-based reinforcement learning to learn to fly together. Consider the case where we have multiple quadrators that are really similar, but the inertial properties are just a little bit different, which could also be seen as the motors need to apply different voltages to hover in an asymmetric way. So they're similar robots, and we think that there should be some generalization across the dynamics. The task is similar, and I want to think that we could learn more rapidly by sharing data. And what we're going to need is we're going to need a different model type where we're conditioning on some data from some set of dynamics data from each of the robot to then share the data. And what I want to do is set this up in a similar experiment to our model predictive control. It looks like I froze. Okay, I'm back. And there's a couple of ways that we could run this experiment. The first way is serial, where we take our first robot and we run it, and then we train a model, and then we take our second robot and we run it and we train a model, and we take our third robot and we do these one at a time. This should work. Hopefully we'll see better data efficiency in this case, but a little bit less inspiring, because where I see this going is a parallel case where you have a lot of robots. In a manufacturing case or a logistics case, you have a lot of robots that are similar, and you want them to learn as fast as possible in both wall time and data point time. So we want to be able to run these in parallel and train the dynamics model, and then you want to run these again and then train another dynamics model, and I call this parallel. We were going to start with the serial case because the controller is easier, but the dynamics model should be working in similar ways. And the deliverable here, building on past work, is going to be a 60-second hovering for 3 quadrators learning together. And there's a condition on the hovering time being 10 times longer, but I want to use a optical flow board that's available for the Crazy Fly, where you have local velocity estimates. And we could add a term to our reward function to make the local velocity estimate 0 and hopefully eliminate drift. And the impact is that we can learn faster by sharing information of similar robots. And as robot learning and robotics scales, we hope to have more robots, and we want to be able to use that data to share them across similar tasks and really increase the rate of this deploying robots to the real world. So to recap, I started with this challenge where robot learning isn't quite sample efficient enough for some tasks that I'm interested in. And I proposed thinking about these models that we're using for the different tasks and whether or not the model is good enough, what we have to change to make the model good enough. And I talked about these 3 deliverables that I want. And I have done a bunch of work that shows I think I'm in the right place to actually achieve this going forwards. And other than the specific publications, I've done other things at Berkeley, like teaching Intro to AI, and been writing proposals with Chris in these internships. And I have a timeline where putting these deliverables I've seen into order is towards actually graduating and writing a dissertation. So over the summer, we're going to submit this new neural network parameterization and to Coral, and then we want to do controlled flight of the Ionic craft in the fall, and then in next spring, submitting this framework for how we could use multiple agents to learn together to NeurIPS, and hopefully graduate in fall of 2021. So at the end, I just really want to say that the high-level goal of this work is to have model-based reinforcement learning algorithms and processes that are ready for real robots, and to remember that all of our models are wrong, but some are useful, and even very wrong models can be very useful. So let's think about how we're using them and where we're going to make robot learning more useful. Thanks. Woohoo. Wow, I was pretty good on time, even though I rushed through some things.
Yeah, you were talking really fast.
Yeah.